Hello, this is John Carney from the National Weather Service in St. Louis, and I have a presentation for you today on some basic radar and satellite interpretation. I'm sorry I couldn't give it to you in person. We've had some bad medical news here, some bad luck at the National Weather Service office, and we're down several members. We're covering sick leave, and we also lost an intern. She went down to the Midland office to continue her career as a forecaster. So we're just short-staffed here, and I couldn't break away from the forecast desk to be out there in Columbia with you today. So I'm real sorry. Hopefully next time I'll be able to get out there. Anyway, this presentation is about 47 minutes long or so. If I start getting long-winded and run out of time there, I suggest you skip to about the last 12 minutes or so of the presentation. It's about a 10-minute long slide, part of the presentation that I go over some nice websites to look at satellite and radar data, sites that you might find useful, and I demonstrate a little bit on how to use them and the kind of things you can display. This is a little background information on weather radar. The first dedicated weather radar that the National Weather Service fielded was the WSR-57. It was fielded in 1957, therefore the 57 in the name. You could only see reflectivity. There was no wind information at all. There was only one elevation scan when the radar was in network mode, meaning all the radars would be mosaic together into a national network of radars. Now you could manually control the antenna to do elevation scans when you wanted to interrogate a specific storm, but normally you would only get the lowest degree elevation, about 0.5 degrees, and that's what you would see on the planned position indicator. So this is old technology, and it has since been replaced with the WSR-88D. So this is the radar that replaced the old WSR-57. It's the WSR-88D, Weather Surveillance Radar 88 for 1988 when the plans were locked down, and the D of course stands for Doppler, meaning it can sense wind direction. It's an S-band radar with a frequency of 2700 to 3000 megahertz, 10 centimeter wavelength on the pulse. Pulse duration is 1.577 microseconds. The pulse length about 500 meters. Peak power of 750,000 watts at the transmitter. The antenna is a 28-foot dish, and it is both horizontal and vertical waveform on the pulses, and beam width of about 1 degree. Here's a few of the advantages of the WSR-88D over the 57. You have a higher resolution and increased sensitivity over the 57, and of course you can detect the movement toward and away from the radar. Have fully automatic volumetric scans of the atmosphere every 5 to 10 minutes. However, there is no manual control of the antenna, so there is no way for the operator to stop the antenna and initiate a sector scan like there was with the WSR-57. All of the volume products from the WSR-88D are fully automatic. Here's a couple of examples of scan strategies that the WSR-88D uses to actually scan the volume of the atmosphere. For instance, on the left here, precipitation mode will actually use 14 different elevations with the antenna going through complete rotations through each elevation in this scan strategy to get you a 3D picture of the atmosphere. On the right here is a clear air mode. It uses just a few elevation scans, just 5 on VCP 32 and 31, but the antenna rotates much slower, so you get a much more detailed picture of the atmosphere in those lower slices. So in VCP 11, the antenna rotates much faster. You get a complete volume scan in about 5 minutes, whereas clear air mode takes 10. There are actually about a half a dozen, or perhaps a couple more, different scan strategies that the WSR-88D can use based on the weather conditions that are going on at the time, and those scan strategies are selected by the operators. I wanted to demonstrate the difference between a single slice reflectivity product and a volume reflectivity product, which I'll show on the next slide. This is an example of a half-degree reflectivity product of some thunderstorms, and this is just one single slice of the storms that are fairly close to the radar. You can see this little diagram here, the single slice going through the storms, and it sees the reflectivity that is nearest to the ground on this half-degree slice. On the next slide here, this is a composite reflectivity, and it's actually seeing the volume of the storm from the lowest slice all the way up through the top slice of the radar volume. And you can see the difference. I'll go ahead and toggle back and forth between the two of them. These are at the same time. The composite reflectivity will actually show the highest reflectivity that the radar is detecting within that entire volume. So sometimes that composite reflectivity can be more helpful, especially with storms that are real close to the radar, because sometimes the radar will actually shoot beneath some of the higher reflectivities that are in the thunderstorm on that lowest elevation slice. So if you look at a composite reflectivity, you can sometimes get a better idea of the strength of the thunderstorms, especially when they're in close to the radar. One of the limitations of weather radar is that it can't really see what's directly above it, and this is just a little diagram to show that in St. Louis, for instance, our radar is within about 20 miles of the city there. It's well within the St. Louis metropolitan area, and we have a difficult time seeing storms that are within that 15 to 20 mile radius because they're above that 19.5 degree slice, which is our topmost slice that our radar will look at. However, the radars in Paducah and in central Illinois, Lincoln, will see storms that are right over the metro area with their half degree and 0.9 and 1.5 degree slices. So we get to have a good coverage over our metro area with those adjacent radars. In central Missouri, the problem is a little bit different. Our lowest slice is 1/2 degree, so it actually will be quite a ways above the ground, about 4,000 or 5,000 feet, because the Earth actually curves away from it, and the radar beam will rise in altitude. So we use a combination of our radar and the Kansas City radar, which is actually located in Pleasant Hill, Missouri, to cover central Missouri. And using our two radars, the St. Louis radar and the Kansas City radar, we do actually have a pretty good amount of radar coverage there in central Missouri. Okay, now we're going to get into a little bit of interpretation and some of the things that can affect what you see on radar. One of those things which affects what you see on radar is the current state of the atmosphere. So in a normal atmospheric lapse rate, where you have warm conditions near the surface and gradually cooling conditions aloft, the radar beam will actually refract through the atmosphere at a very predictable rate. So you can actually tell with some pretty good accuracy how far above the surface the radar beams will be intercepting storms. Now, when you have, let's say, a very warm day with very warm conditions near the surface and much cooler conditions aloft, the radar beam will refract at a lesser level. So the radar beam will actually be rising in altitude more quickly than under normal conditions. When you have an inversion, the radar beam will actually bend back towards the Earth's surface, so it will actually be closer to the ground than what it would be under normal conditions. And if you have a very strong inversion, the radar beam will actually bend right back towards the ground, and you'll actually be hitting the ground with the radar beam instead of hitting your atmospheric targets. It's kind of like when you put a straw into a glass of water and you see that straw, it appears like the straw is cut in half. The same thing happens with our radar beam when you have a very strong atmospheric inversion. It actually just bends the electromagnetic radiation from the radar beam right back into the surface of the Earth. So what can happen sometimes with that really strong inversion and the ducting that occurs is the radar beam will actually bounce back and forth along the ground, and that really strong inversion. And it's a very particular looking kind of reflectivity signature when you look at it on the indicator there. You can see spikes of high reflectivity going down each radial, and it doesn't move when you loop the image. It just kind of sparkles. The individual radar pixels will increase and decrease in intensity from image to image, but the whole pattern itself will actually not move, and it'll just kind of sit there and sparkle. And these reflectivity signatures can look really ominous to somebody who isn't used to looking at radar data on a routine basis, but once you've seen it once, you can identify it every time. And if you ever see something like this on radar, it's nothing to be concerned about. You can always call the weather office that is running that particular radar and ask them if it's anomalous propagation. But we don't usually see it much anymore because radar algorithms have improved quite a bit over the past 10 years or so, and our radars can usually filter this stuff out. But occasionally there's a really, really strong inversion, and we can't actually filter that out. So if you ever see it again, you can call the weather office and just ask them if that's anomalous propagation, and hopefully they can mitigate that in the radar data for you. Something else you'll see in clear air in radar data is ground clutter. Now, we were talking about before that anomalous propagation technically isn't ground clutter. It's something that appears, under certain atmospheric conditions. Ground clutter is something that you'll get almost all the time on radar, close into the radar, usually within a few miles. We do have clutter filtering algorithms on our radar, but they do fail in certain circumstances, like if that ground clutter is moving. For instance, if the radar beam is shooting down a interstate highway and the radar detects movement of the cars back and forth on the highway, the clutter filtering algorithms will actually fail because the radar thinks that it's actually seeing meteorological targets instead of the ground clutter. This is a close-in shot of the ground clutter pattern on our radar here in Weldon Spring. You can see very clearly Highway 64 and US 61 headed up towards Hannibal, Highway K going into O'Fallon, Highway 94 and also 364 headed into St. Louis. And we're able to see these roads because cars are traveling on them, and the radar thinks that it's actually moving meteorological targets instead of cars on the highway. And we see this all the time, and a lot of radars in the country have this problem as well. It's just something that we learn to deal with. For instance, the Highway 364 here, we get tornado vortex signatures on it all the time, and that's because you have inbound and outbound cars headed straight towards the radar, and the radar thinks that it's seeing a tornado vortex instead of cars moving on the interstate. So we occasionally get alerts on that. It's a sort of a semi-permanent feature that we've just learned to kind of filter out ourselves. Something else you get in clear air, and actually all the time on radars, are interference spikes. And it's basically just a radio source that's very near the same frequency as our radar. As the antenna sweeps past that source, you get this long filament or spike in the direction that the radio source was. This was a wireless broadband interference spike that was on our radar for several years. We finally got it filtered out. Every day also we get sunrise and sunset spikes, because the sun, of course, radiates all across the EM spectrum, and when our antennas align with the sun during sunrise and sunset, you get these interference spikes, and you can just watch them march across the country as the sun rises and sets. Biological targets are something else we pick up on radar. This is a bird ring that actually formed on the Chesapeake Bay, being picked up by the Sterling, Virginia radar. You can see it here starting to form, getting larger and more well defined here in the second image. And the third one, it's actually pretty huge. It's one of the largest bird rings I've seen. Has a sunrise spike through it too, so this is actually something you see a lot during sunrise, especially during the migration season. We pick up birds and bats and bugs and all kinds of other critters on radar. Again, it's just something that for your information, if you see something like this, it's not a weather hazard that you need to worry about, just something that our radars happen to see. And again, if you have any questions about something you see on radar, just call the weather office and we can help you identify it. We'll occasionally see military chaff on radar as well, and sometimes it can be a little bit difficult to identify because it does kind of look like a meteorological target, but it will usually align itself with the mean flow, and in this case the wind is either moving from sort of east-southeast to west-northwest, or in the opposite direction, west-northwest to east-southeast. So it'll be kind of along that mean flow there at whatever level of the atmosphere that the chaff is at. Typically you can identify it by looking at satellite pictures as well to see if there's any clouds associated with the lines that you're seeing on radar. And sometimes that works, sometimes it doesn't. Sometimes there's clouds there that obscure what you're looking at. But anyway, again, this is a clear air kind of target that we'll see sometimes. And when you start seeing these lines like that in the radar data, especially fairly well aloft, this is being looked at from a Florida radar, and you can see these lines of chaff are actually quite a ways away from the radar, so it's probably at least 6,000 or 7,000 feet up in the air at that point. Low-level jets are something else you can see on radar. In this case, we had a low-level jet moving from the south-southwest to the north-northeast. This is a plan view of velocity. Greens are inbound towards the radar, reds are outbound. This is again a 50-knot low-level jet right about 5,000 feet off the ground. This is something you can look at if there are enough targets in the air to for the radar to pick up at those levels. In this case, it was a fairly warm, moist air mass, and we had some clouds around, so it was pretty easy for the radar to pick up those winds. However, if it's a cold, dry air mass and there aren't any clouds, lots of times there aren't enough scatterers for the radar beam to bounce off of, so we won't be able to actually see these signatures. But in the springtime, this is a good thing to look at in the morning. Just when you're looking at radar data on the internet, switch over to velocity and see if you can see this kind of pattern, and you'll know that there's a strong low-level jet that morning. So we've been talking about a lot of non-meteorological signatures on radar. This one's actually something that's weather-related. We will also see Altocumulus castellanus on radar, and it's something that you should be concerned about because lots of times we'll have a dry forecast in the morning there, or maybe just a 10% or 15% chance of rain. And sometimes in the springtime we'll get just enough elevated instability to get these Altocumulus castellanus or ACUS clouds to get going, and we'll get some light showers that will actually fall out of them. They're real spotty. This is what it looks like on radar, just real spotty little things. They're right around sunrise. Lots of times in the office we call it sunrise surprise, because we're really not expecting much in the way of instability or precipitation, and the low-level jet will actually bring in just enough instability and just enough moisture to get these few little spotty showers. And I mean, sometimes it can actually touch off a couple of lightning strikes as well. But it's something to be concerned about. If you see these little spots starting to develop on radar, maybe just before sunrise or right around sunrise, and you can actually see the ACUS going there with those kind of bumpy, turreted kind of tops to them. You'll get these little showers going, and they can certainly ruin a flight if one of them happens to intercept you there. Something else that the radar sees is Verga. It looks like a donut around the radar. That's because the radar beam is rising away from the antenna. It's passing through the precipitation on its way, out into outer space there. But the precipitation isn't hitting the ground here. It's falling through a dry layer, and it's all evaporating before it hits the ground. So that's why we're not seeing the precipitation closer into the radar. I mention this because a lot of times we'll have a dry forecast going when there's Verga around, and that's because we only forecast precipitation that hits the ground. That's when we have the chance for precipitation. So if we have a dry forecast going and you see this signature on radar, just be aware there's actually some precipitation aloft. It's just not hitting the ground. You can see cold fronts on radar as well. They look like fine lines that are moving across the radar screen, usually from northwest to southeast or west to east. Cold air coming down from the north. You're actually not seeing the front per se. You're seeing the stuff that the front is kicking up. So if there's a lot of dust or bugs or things in the air that are actually being pushed along by the cold front, that's what the radar is actually picking up. And again, it looks like a fine line in the radar data that is a nice contiguous line of reflectivity, of a higher reflectivity that's moving, as I said, usually from west to east or northwest to southeast. Another fine line that you can see in reflectivity are outflow boundaries. Let me see if I can get this moving again. So you can see in this loop you have that fine line of reflectivity that's moving away from the thunderstorm. You know, this is the outflow from the thunderstorms that's moving away in like a nice, usually in a nice ring pattern away from the storms. Sometimes if you have a line of thunderstorms that's moving through an area, the line will move out, the outflow boundary will move out ahead of the actual line of thunderstorms by several miles. Again, this is a pretty serious threat for you guys. The outflow boundaries signify a pretty significant wind shift. Can be violent at times, if you have a real strong thunderstorm. So that's something to be aware of. Look for the fine lines on radar data, especially when there's any thunderstorms in the area. Horizontal convective rolls also show up in reflectivity data. They look like sort of densely packed lines of higher reflectivity interspersed with lines of lower reflectivity. They line up along the mean wind flow. So in this case, you have a southeast wind. The horizontal convective rolls are lined up from the southeast to the northwest. And I bring this up because they can pose a threat to aviation. What you get these rolls of instability that will cause little cumulus to form, and often you'll see the horizontal convective rolls in the radar data before the cumulus will actually form. There'll be gravity waves associated with these. Also some fairly significant updraft and downdraft sort of couplets within the atmosphere. So it's something to take into account if you're planning an afternoon flight. If you see these horizontal convective rolls, might be something you want to pay closer attention to. Okay, we're going to move on to some satellite interpretation here. This is a visible satellite picture taken of the Midwest. You see Lake Michigan here, St. Louis down here in the bottom center of the screen. Columbia's out here off to the left. A lot of snow on the ground. You can easily see all the river valleys where the snow's fallen, and bare ground down here to the south of St. Louis. Here's a diagram of our geostationary operational environmental satellites, or GOES satellites. It's about 27 meters long, which is right around 90 feet from the end of the solar wing there out to the other end of the satellite. The instrument package is quite a bit smaller, but it's packed with all kinds of communications equipment as well as imaging sensors. A lot of our weather data actually gets sent up to the GOES satellites from ground stations and then beamed back down to the forecast offices, 122 forecast offices across the country. And as I say, a bunch of the weather data that we ingest at the offices comes to us, straight off the GOES, bounced off from ground stations. This is the basic visible satellite picture, full disk image that all weather satellites have been taking since the early 1960s. We take one of these full disk images every 2 to 3 hours, and the rest of the time the GOES East satellite is focused in more on North America and various sectors of the tropics, and also the United States. When there's severe weather, they have a floating sector that takes very high resolution images. The reason we don't take the full disk image as often as we otherwise would is because it does take a lot of bandwidth to send that image down to the ground stations. And when we're in severe weather operations, we need all the bandwidth we can get so that we can get imagery, high-resolution imagery, as frequently as every 5 minutes from the satellite. We have 3 primary channels that our satellites take pictures in. The first is visible, and it's just like sitting out in space with a digital camera and taking a picture of the Earth. We get these pictures as frequently as every 5 minutes when we're in severe weather operations. For research purposes, they can even get it in every 1 minute. The imagery has a resolution of 1 kilometer, so each pixel on a grid across this picture is 1 kilometer on a side. The second channel is infrared, and that measures the temperature that the satellite is seeing. This is a picture of a supercell thunderstorm with the very cold cloud tops. Looking at the scale down here, 80 degrees below zero, looks like on this overshooting top right here. You can see again the overshooting top where all of this surrounding cirrus blow off from the thunderstorm is actually a little bit warmer than where the top is. This is an indication of a very, very strong updraft right there in the center of that overshooting top. It's actually rising much higher than the rest of the surrounding cirrus. You can even see these little waves in the cirrus here. Those are gravity waves that are propagating out from the overshooting top as the top actually goes well up above the surrounding cirrus and then collapses in a downdraft and then shoots back up again and then collapses. You get this wave-like motion on the cirrus clouds around it. The third channel that we routinely get from the satellites is water vapor, and water vapor imagery is basically a representation of the height of a certain amount of water in the atmosphere. And it's a type of infrared imagery that is actually collected by the satellite. We use it to track waves in the atmosphere that actually produce the sensible weather that we see at the surface. This is a water vapor loop here, and I just wanted to show this so that you can get an idea of what we see in real time when we're getting this water vapor imagery. You can see it's a really good representation of some of the fluid motions of the atmosphere. This is an actual shortwave that, if you ever read our forecast discussions, that's what we call a shortwave. You see that it's like this eddy that is moving through the atmosphere, and it's producing weather as it goes. And we can use these water vapor loops to help us track these things and try to figure out where they're going. And by the way, this data is all also ingested into our models, and it helps them get more accuracy in trying to figure out this sort of chaotic fluid motion to the atmosphere. If there aren't any clouds and you can see straight down from the satellite to the surface of the Earth, you can use satellite imagery, the infrared, to actually track cold fronts as they move through. And this is a cold front passage down through Texas and Oklahoma, and you can see the cooler air as it spreads south here along this line. And what I think is actually pretty cool is this was a pretty clear night, and the lakes here in Texas and Oklahoma show up as darker spots as the cold air moves over them. So the water is warmer in those lakes than the air surrounding it, and it's really easy to pick them out. It looks kind of like Swiss cheese here to me. And again, yeah, this is kind of a neat image of a cold front moving south through Oklahoma and Texas. Earlier we talked about seeing outflow boundaries on radar. You can also see them on satellite. This is a satellite picture, visible satellite picture from the Caribbean and Gulf of Mexico. Here's Cuba, and here are the Florida Keys, the Straits of Florida right here. Each one of these little loops here on the satellite picture is a outflow boundary from thunderstorms that are ongoing here in Cuba. A lot of times these outflow boundaries on satellite picture are actually marked by a lack of clouds. Each one of these clear slots right in here is a place where a thunderstorm had formed and then dissipated down here as well. The thunderstorm blew up and produced the rain and cooler air, and then collapsed. And this is basically just a little bubble of cooler air left over by the thunderstorm that collapsed, and that's why it doesn't have any clouds in the center. So the outflow boundary is out here just on the periphery, and you can see probably new convective development trying to take place here on the western side of this outflow boundary. I want to revisit the overshooting tops on thunderstorms here. This is a satellite picture of some thunderstorms over eastern Iowa, and you can see the overshooting tops here where just to the west of where these shadows are. You can even see some of the gravity wave action in the cirrus clouds from the overshooting tops. Here's some more down here on the southern storm. It's just a good idea to keep this in mind, that these storms do produce gravity waves and outflow boundaries that can be seen on satellite and on radar as well, and they can move outward from storms for many miles, and it's just a good idea to know where the storms are and understand that the effects of the thunderstorms can be felt for many miles away from the thunderstorms. So just take a look at the satellite imagery and keep in mind where those storms are if you're planning a flight anywhere within a good distance from the storms. Here's just another look at some overshooting tops on infrared picture here. Very cold cloud tops here. Looks like on the order of, again, 70 to 80 degrees below 0 Celsius, with the warmer cloud tops around them. This is what the meteorologists call an enhanced V signature, because it actually does look a little bit like a V. In this case, it looks like a U. But when you start getting those enhanced V signatures around the overshooting tops, it's a sign of some very strong updrafts in the thunderstorm. It's probably a severe storm with large hail and high winds, in excess of 60 miles an hour. So again, this is just a beast to stay away from if you're ever thinking about planning a flight. Wanted to show you real quick a few sites where you can look at some radar and satellite imagery. My absolute favorite site for satellite imagery is the GHCC site from NASA, and I'll go ahead and show that to you now. When it comes up, you get a choice of infrared or visible or water vapor imagery from goes east and goes west, full disk imagery, and there's some also global imagery as well. I'll just show you how to use the site here real quick. It's a little bit of a learning curve, but it's not too bad. You can do a single image. Just click on the sector you want to look at, and it'll bring up a single image. Or you can do an animation, and I'll go ahead and do a 12-frame animation here. Good high quality and a high zoom factor. When I make the image large here, hopefully my computer can keep up with showing you this satellite loop and also recording as well. So here you go. This is a satellite imagery from today. Good high resolution imagery, as good as we get here in the office. A little bit of snow on the ground. Have some mid and high clouds moving through Iowa. And if you look closely, you can actually see the snow starting to melt away back here over central Missouri. And that's due to some warmer temperatures and some southwest winds we've had today. Now going back to the slide real quick, we'll look at some one of the radar sites that I like. Radar.weather.gov. That's the basic site for radar. I'll show it to you real quickly. This is what it comes up with. And you can select any radar site across the country, or you can look at mosaics. Unfortunately, the mosaic for our part of the country sort of cuts off right here in Missouri and Illinois. It's not my favorite site for looking at mosaic radar data, but you can drill down and look at any radar site that you like, and move with the arrows back and forth from, let's say, Kansas City to St. Louis, and you can look at velocity. There's not a whole lot on radar today because it's a clear day. The other site is the enhanced data display, preview.weather.gov /EDD. And this is a neat site, although it's experimental, so it's not operationally supported. I have to say, though, it's been very reliable for me, and I like to use it almost exclusively to look at mosaic radar data. And when you first pull it up, it's a little dense, okay? It's got a lot of information on it. But if you just want to look at some radar data, the radar icon up here has several buttons next to it. I'll go ahead and zoom in a little bit. And I kind of like to change the map so it's a little bit easier to see certain things. And I'll turn on the radar data here. You can see it's popped up. And you can make it you can actually make it less or more transparent with this slider bar here. And I also like to overlay the states, because if you don't overlay the states, the radar data will actually cover up the state boundaries, and it's hard to kind of figure out where you are sometimes. This is a pretty quiet day for a change across the continental United States. It would be on a day that I'm actually trying to give a presentation on radar. But you can look at radar data here in a mosaic, or you can select individual radar sites, and they'll pop up here. If you click this button, it'll bring up the individual radar sites, and you can select that and do high resolution base reflectivity, and it'll load up here. And it is somewhat more high resolution than the mosaic radar data. I have to say it's not as good as some of the data that you can get online, but it's pretty good. You can loop it and change the opacity of the radar data. Let me turn that off so we only get, there we go. You have several different products, including some dual pole products. The dual pole products probably aren't very useful to you. You probably just want to stick with reflectivity and velocity. Yeah. So anyway, that's the EDD. Looking at radar. Now you can do all kinds of good stuff with this besides just radar. If you want to, you can look at satellite data. I'll go ahead and turn that on. And it defaults to a infrared satellite picture, but you can change it over to visible. So there you go, there's your visible. Change the opacity of the visible satellite there. Doesn't seem to want to work for me. Right there we go. Can go ahead and loop it. Now it's not going to have as many. It's not going to be as detailed as the GHCC site. It's the number of images is going to be less. it'll only give you the number of hours that you select here with this little button. However, if you want to get something that's has a higher temporal resolution, meaning every 15 minutes or every 5 minutes, depending on if the satellite is in regular scan or rapid scan, you want to go to that GHCC site, and you'll get the same data that we're seeing here in the office from GHCC. You can also look at our hazards. If we have any winter weather advisories or flood advisories or anything like that out. Zoom out here, and we don't have anything in effect here for Missouri and Illinois, but down here we've got red flag warnings, which is a fire weather advisory. Looks like frost advisories and things down here issued by some of our southern region offices. So you can see those when we have any kind of weather advisory by turning on that hazard display. You can look at models and other things, change the background to several different kinds of maps, and whatever suits you. You can look at, let's see, observations from the surface. These are just sort of surface airways observations, usually taken at airports, but sometimes they're taken at we're ingesting the data from lots of different sources, so it may not be just airports that show up. And if you hover over the observation there, it'll actually give you the information, and you can look at a graph of what the temperatures have been doing and dew points and winds and everything. So it's a pretty neat site, and as I said, it's not operationally supported, so if it does go down, it may be down for a while because they actually have to call somebody in to fix it, or they may not actually call someone in. They may just wait until that person who's been working on this display comes in for their regular shift. But it is a pretty neat site, and it has been very reliable for me. Okay, just wanted to say thank you. That's all I've got for you. And apologize again for not being able to make it out this year. Hopefully we'll see you next year when we're fully staffed again. And just want to say, have a safe and hopefully fun flying season this year. If you have any questions, my email address is there on the screen, so please feel free to email me anytime. Thank you very much.